Welcome back to your statistics class. My name is Jacqueline Lashuga and I'm going to be your instructor for today's lecture. Last lecture you learned about the null hypothesis significant testing and the t-test. Today we're going to continue talking about these topics. As always, we'll begin by reviewing some of the material that was covered last class. Last time, we talked about sampling distributions of statistics other than P and the sample mean. We specifically said that these other sampling distributions are not necessarily normal. For example, here you can see the sampling distribution of R when rho, the correlation between two variables in the population, is equal to 0.90. As you can see, the tail is really long towards the left, but is really short towards the right. And this is because R cannot exceed a value of 1. We also mentioned that the expected value of these other sampling distributions is not necessarily the same as the parameter in the population distribution. Here we have, once again, the sampling distribution of R when rho equals 0.90. Rho is being indicated by the red line, while the expected value of R is being indicated by the green arrow. Now, as you can see, the expected value of R is actually lower than 0.90, showing us that there is an underestimation of the true correlation in the population. We also spent some time talking about the sampling distribution of the standard deviation, and we said that this distribution is normal if the sample size is equal to or greater than 30. However, we also said that the expected value of the standard deviation in the sampling distribution is less than sigma, the standard deviation in the population. This means that the standard deviation tends to be slightly too small. It underestimates sigma by just a little. During the last lecture, you learned how to calculate sigma hat, an estimator of the population standard deviation. This estimator is also sometimes called S, and it includes a small correction to the usual standard deviation. The correction involves using n minus 1 instead of n when you divide the sums square to get the mean square. You will run into this correction when you take the advanced statistics course. For this particular class, you will not be using this correction. Instead, you're going to plug in the standard deviation when you need an estimated value of sigma. For instance, when you're calculating the standard error of a sampling distribution. Another topic that we covered last class was the two-group studies. We said that in this particular studies, we compare the means of two groups on one dependent variable. And we talked about this specific example where we are comparing the mean IQ scores of men and women at Culver University. The mean IQ score for women was 106, and the mean IQ score for men was 104. But then the researcher faces this question: is it possible that the two populations have the same mean? In other words, is it possible that this 2-point difference between men and women in the sample is due to sampling error? These two dots represent the means of the two samples we just talked about. The dot on the left shows the mean IQ 104 in the men's sample, and the dot on the right shows the mean IQ 106 in the women's sample. This line is showing the confidence interval of mu around the sample mean of the men. The confidence interval indicates that the population mean for men at the college is likely to be between 101 and 107. This is the confidence interval for the women's sample. As you can see, 105 is a likely value of mu for both of these samples. Therefore, it is entirely possible that there is no real difference in the populations. The 2-point difference between these sample means could be due to chance, could be due to sampling error. It may not indicate a real difference between the populations, and it is not statistically significant. All these statements are ways of expressing the same underlying idea. We also talked about this example where we are doing a two-group study that compares students with a 2.0 GPA and students with a 4.0 GPA. The mean IQ in the sample of 2.0 students is 100, and the mean IQ in the sample of 4.0 students is 110. Again, the researcher has to face the question, is it possible that the two populations have the same mean? In other words, can sampling error account for the 10-point difference between the samples? Here we have the two samples. And now you can see the 95 confidence intervals around each sample mean. As you can see, the possible values of mu for each sample are very different. There is no overlap in the confidence intervals. The 10-point difference between sample means in this example is probably not due to chance, is probably not due to sampling error. It probably indicates a real difference between the populations, and it is statistically significant. Again, all these are ways of expressing the same underlying idea. And this is a problem that researchers always face when evaluating the results of a two-group study. In a two-group study, there is always going to be a difference between sample means. So how does the researcher decide if this observed difference between sample means is statistically significant, that it reflects a real difference in the underlying population? Well, the answer to this is the null hypothesis significant testing. And the t-test happens to be the form of null hypothesis significant testing that is used in two-group studies. To understand the t-test, it's first necessary to understand the sampling distribution of the difference between two sample means when the null hypothesis is true. Here's the symbol for the difference between two means. It shows the mean of the first sample minus the mean of the second sample. So we can replace those words with this symbol. Now here is the equation that represents the null hypothesis. Mu1 equals mu2. That is, the mean of the first population is equal to the mean of the second population. This second equation is equivalent to the first one and can also be used to represent the null hypothesis. And this is also a symbol that can represent the null hypothesis, a capital H with a small subscript of 0. The 0 means null. So we'll replace the words with the symbols. We could use any of the three symbols that represent the null hypothesis, but this symbol makes it clear that we're focusing on the difference between the two sample means and the difference between the two population means. There are 6 steps to creating this sampling distribution. The first step is to begin with two populations, and we'll refer to them as population 1 and population 2. The second step is that the two populations must be the same. Or to put it in another way, the difference between them must be 0. Or to put it in another way, the null hypothesis must be true. The third step is to collect a large number of paired samples. You collect one sample from population 1, and this sample is referred to as sample 1. You collect another sample from population 2, and this sample is referred to as sample 2. The fourth step requires that each pair sample contains n individuals from population 1 and n individuals from population 2. The number of individuals in sample 1 must be the same as the number in sample 2. The fifth step requires that for each pair sample, you calculate the difference between the two sample means. So for instance, if the number of samples, k, is 10,000, you will end up with 10,000 numbers. Each number represents the difference between the two means in a particular sample. Finally, you would make a density histogram of all these values. And this density histogram shows your sampling distribution. Like all density distribution, its area is equal to 1. Now, this particular sampling distribution has some features that are worth talking about. The first concerns its expected value. If mu1 minus mu2 equals 0, that is, if the null hypothesis is true, then the expected value of the sampling distribution is 0. And we can tell that just by looking at the histogram. So this red arrow is pointing towards the mean of this distribution, which is equal to 0. The second thing to notice is that the sampling distribution is normal in shape if n, the number of individuals in each sample, is 30 or more. The third thing worth noticing is that the values of the difference between the two means that are close to 0 are more common. But values of the difference between the two means that are far from 0 are uncommon. For instance, the height of the bars in the distribution show us that 0 is the most common value of the difference between the means. Also, values from -2 to +2 are common. However, it is very uncommon that the difference between the two means is 5 or higher. Okay, so we are now ready to move on to the new material for today's class. Again, today we're going to continue talking about the null hypothesis significant testing and the t-test. Everything that you have learned about the sampling distribution of the difference between two means has prepared you for what you're going to learn today. As I have mentioned before, in a two-group study, the sample means are always going to be different. And a researcher has to consider two possible explanations for this difference. The first explanation is that this difference may be due to sampling error. The second explanation is that the difference in the sample means indicates a real difference between the underlying populations. And to be able to decide which of these two explanations is correct, the researcher can do a t-test. And now I'm going to show you how to do a t-test. There are 5 steps for us doing this. We're going to be using the same example as before. We have 2 samples, men and women at Culver University. The mean IQ for the woman is 106, and they're sample 1. The mean IQ for the man is 104, and they are sample number 2. The standard deviation of IQ score is 15 for the woman and 16 for the man. The first step in doing the t-test is to conditionally assume that the null hypothesis is true. That is, at the beginning, you assume the two population means are equal. Now, this may seem like a strange assumption. After all, the researcher probably hopes the population means are different because that's interesting and the researcher can write it up and maybe get an article published, get tenure, and live happily ever after. But, as you will see, it is useful to start with the assumption that the null hypothesis is true. And this assumption is only conditional. That is, the assumption is only made for the moment for purposes of exploration. If later the researcher decides that the population means are not equal, she can change her mind. The second step requires the calculation of 3 numbers: the observed difference between the means, the expected value of the sampling distribution for the difference between two means, and the standard error of that same distribution. Today we're going to be learning how to calculate all these three numbers. And we're going to start with this number right here. This is the symbol for the observed difference between the sample means. These are the results of the study that I showed you earlier. What is the observed difference between the sample means? Well, here is the math. The two means are 106 and 104. 106 minus 104 is equal to 2. So the difference between the two means is 2. So we have now calculated this first number and we'll move on to the second. The next number that we will calculate is the expected value of the sampling distribution. What is the expected value of the sampling distribution of the difference between the two means? Go ahead and take a couple of seconds and think of this answer. I'm going to give you a hint. Our first step was to conditionally assume that the null hypothesis is true. Take another couple of seconds and think of your answer. Well, I am now giving you a second hint. If the null hypothesis is true, then the expected value of the difference between the means is 0. In the first step of the t-test, we assume that the null hypothesis is true. So what must the expected value be? The expected value of the sampling distribution is 0. And when we do a t-test, the expected value is always equal to 0 because we make the assumption that it is 0 in the first step. So now we're ready to calculate this third number, the standard error of the sampling distribution of the difference. And there are three ways to calculate this number. The first one is that we can make an estimate of the standard error. The second is that we can use this formula to estimate the standard error. Or third, we can hope that some really nice person tells us the standard error. Let's go ahead and try the first way, which is estimating the standard error. As we learned in past lectures, if we have the histogram of a distribution, and if the distribution is normal or normal-ish, then we can estimate the standard deviation of the distribution from the histogram. In this case, we can estimate the standard error from the histogram since the standard deviation and standard error are practically the same thing. So, I want you to look at this histogram and make your own estimate for the standard error. Go ahead and take a couple of seconds and then come back to the lecture. Your estimate should be that the standard error is about 2. So give yourself some credit if you were close to this answer. When we're making an estimation, we first want to estimate the score at the mean and the score at the 97.5 percentile. In this histogram, the mean is about 0 and the score at the 97.5 percentile is about 4. We know that the distance between 0 and 4 is 4. We also know that 0 and 4 are about 2 standard errors apart because 0 is the mean and 4 is at the 97.5 percentile. So 4 is equal to 2 standard errors. If 4 is equal to 2 standard errors, then 2 is equal to 1 standard error, and that is going to be our estimate. So, this is one way in which you can estimate a value for the standard error by using your histogram. We made an estimate, and the standard error is approximately 2. But again, this is only an estimate. And as a good statisticians, we always want to be as precise as possible. So how do we get the exact value of the standard error? So the second way for us to estimate the standard error is using this formula right here, which is kind of really crazy and complicated. So we're not going to be doing this, but this is something that you're going to be learning in your advanced statistics class. So let's go ahead and use the third method of finding the standard error. And this third method is really easy because some really nice person like me is going to tell you the value for the standard error. And here it is. The standard error is 2.19. Notice that this exact value is really close to the estimate we got by looking at the histogram. That is telling us that our estimation method was pretty good. And how did I get this number, 2.19? Well, I used the formula that I showed you a minute ago. In this class, on the homework and on the test, you don't have to worry about that formula. Whenever you need the standard error of the difference between the two means, I'll just give it to you like I did now. I don't expect you to learn the formula in your first statistics class. This is something for you to look forward when you take an advanced statistics class. So let's go back a little bit to where we were a minute ago. We needed three numbers, the difference between the sample means, the expected value, and the standard error. Now we have all three numbers. And notice how easy it really was. Finding the observed difference between the two sample means was easy to calculate. The expected value of the sampling distribution is just 0, and it will always be 0. And finding the standard error of the sampling distribution was also easy because I gave it to you. So now we're ready for the third step. And that is to calculate a t-score. Specifically, in this step, you calculate the t-score for the observed difference between the means in the sampling distribution. And you might be thinking to yourself, what is a t-score? Well, the t-score is approximately the same as the c-score. In fact, for most practical purposes, it is equal to a c-score. For samples of 30 or more, the t-score and c-scores are virtually identical. So most of the time when you see a t-score, just think c-score and you will be right. A c-score tells us this. Where does the score of this individual fall in relationship to the scores of other individuals? For example, if an individual has a c-score of 0, we know that their score falls right in the middle of the scores of other individuals. Their score is average. If an individual has a c-score of 2, we know that their score falls very high in relationship to the score of other individuals. And if an individual has a c-score of -2, we know that their score falls very low in relationship to the scores of other individuals. The t-score tells us practically the same thing, but it is about the observed difference between the means. A t-score tells us this. Where does the observed difference between this pair of means fall in relationship to the differences between other pair of means? You may remember that when we created the sampling distribution, we calculated the difference between the means for 10,000 pair samples. The column on the right side of the slide contains the difference between the means for 10,000 samples. So the question the t-test addresses is, how does the observed difference between sample means in our study compare to these 10,000 other differences? As you recall, in step 2, we calculated the observed difference between the means in our study, and we got 2. So here is where the observed difference between the means falls in relationship to all the other differences between means for all 10,000 pair samples. Now, at the bottom of the distribution in red are the c-scores, which are also the t-scores. So what is your estimate for the c-score when the observed difference between the means is 2? Go ahead and take a couple of seconds, pause the video, and then come back to lecture. The t-score is approximately equal to the c-score, which is approximately equal to 0.90. So now that we have our estimate, let's go ahead and calculate the exact t-score. And here is the formula that we're going to be using. It looks a little scary, but I promise it isn't that bad. All we really need are the numbers that we calculated in step 2. So let's take a look at the numerator. It includes the expected value of the sampling distribution of the difference between two means. And what is the expected value equal to? Go ahead and take a couple of seconds and think of your answer. Yes, the expected value of the sampling distribution is just 0. So let's plug this in. We are subtracting 0. And when you subtract 0, it doesn't really change anything. So then we get this. It's a fraction. The numerator of the fraction is the observed difference between the means, and the denominator is the standard error. The t-score is simply the observed difference between the means, the numerator, divided by the standard error of the sampling distribution, the denominator. All we need are those two numbers, and we got those two numbers in step 2, so we have to just plug them in. So what is the observed difference between the means of the two samples in our two-group study? Go ahead and take a couple of seconds, go get your answer, and then come back to lecture. The observed difference between the means in our samples is just 2. So now we're down to the standard error of the sampling distribution, and I gave you this number earlier in the lecture. I told you that the standard error is equal to 2.19. So what is the value of t? Go ahead and take a couple of seconds, pause the video, and get the value of t using the formula above. T is equal to the observed difference between means divided by the standard error. So it's 2 divided by 2.19, which gave us an answer of 0.91. And this t-score of 0.91 actually matches closely our previous estimate of 0.90, which we calculated just by looking at the histogram. So now you know how to do this calculation, but it is important that before we move on, we review some of the underlying logic of the t-score. Now I've said multiple times that a t-score is a z-score or practically the same as a z-score. And here is the formula for the z-score. The little x in the numerator is the score of a particular individual. For C, you start with a score of one individual in a distribution of individuals. Then you subtract the mean. And then you divide by the standard deviation. For T, you practically do the same thing. You start with one observed difference in a distribution of differences. You subtract the mean, which is called the expected value. And then you divide by the standard deviation, which is called a standard error. So as you can see, T and C are based on the same underlying idea. This is why earlier in the course I said that z-scores is a very important concept to learn because it's something that's going to continue popping up in different topics for this class and for future advanced statistics classes that you take. The fourth step is to identify if our t-value falls in the critical region. And the critical region is defined as the 5% of the least likely t-scores. So here's our sampling distribution. The red vertical lines are two standard errors above and below the mean. Anything between them represents the 95% most common scores. That is, 95% of the samples in the distribution have scores between these two bars. Only 5% of the sample fall outside the bars, and these are being shown to you with the yellow arrows. We say that they lie in the critical region. These are the least likely of all the t-scores. And here is our t-value of 0.91 in the distribution. Does this value lie in the critical region? It doesn't. It actually is far away from the critical region. If our t-value falls in the critical region, our p-value is lower than 0.05. This p stands for probability, and p less than 0.05 means that our t-value lies in the 5% of least likely scores. If the answer is no, our t-value does not fall in the critical region, then we say that p is greater than 0.05. And p greater than 0.05 means that t does not lie in the 5% of least likely scores. In our example, t equal 0.91 is not in the critical region. Therefore, we say that p is greater than 0.05. In the fifth step, we decide if our results are significant or not significant. If p is less than 0.05, the observed difference between means is statistically significant. But if p is greater than 0.05, the observed difference between means is not statistically significant. In the example that we have been working with, was the 2-point difference between men and women statistically significant? For a 2-point difference, our t-value was equal to 0.95, which gave us a p-value that is greater than 0.05. The difference is not statistically significant. So let's review some of the reasoning process underlying step 5. We said that the researcher has to decide whether the observed differences between the sample means is due to sampling error or instead indicates a real difference between the populations. The steps of the null hypothesis significant testing allow us to evaluate the first possibility, that the observed difference between means might be due to sampling error. In the null hypothesis significant testing, we assume that the null hypothesis is true. Then, we examine whether the observed difference between means is likely, assuming the null hypothesis is true. This is the sampling distribution of the differences between means if the null hypothesis is true. Would you say a t-score of 0.91 is pretty likely or not very likely? Yes, a t-score of 0.91 is pretty likely if the null hypothesis is true. So we accept the null hypothesis. That is, we conclude that yes, the results of the study are consistent with what we might expect if the population means are the same. Let's quickly look at an example where the p-value is less than 0.05. We will use another example that we are already familiar with, and that is the study that is comparing two groups of students. One group of students with a 4.0 GPA and another group of students with a 2.0 GPA. We are interested in knowing if the differences in IQ are significant or not. The mean IQ for the 4.0 GPA students is 110, and the mean IQ for the 2.0 GPA students is 100. So here's the formula for T. It's the observed difference between the means divided by the standard error of the difference between the means. So let's go ahead and compute the numerator. What is the observed difference between the means? Yes, it's 110 minus 100, which is a difference of 10 IQ points. And here is the standard error. Remember that I have already given you the value for standard error, which is 2.19. So what is the value of t? Go ahead and take a couple of seconds, pause the video, calculate the value of t using this formula, and come back to the lecture. T is the observed difference divided by the standard error. That is 10 divided by 2.19, which gives us a t-score of 4.57. Here is our t-value of 4.57. Is our t-value in the critical region? Yes, it is, right? Is p less than 0.05 or p greater than 0.5? Well, if it is in the critical region, then p less than 0.5 is the correct answer. A t-value of 4.57 is a pretty unlikely value if the null hypothesis is true. Thus, the null hypothesis must be false. So, we reject the null hypothesis and we accept the alternative hypothesis that the two population means are not equal. The symbol for the null hypothesis is a capital H with a little subscript of 1. That is all for today. This is going to conclude our lecture. Thank you very much for listening to me, and I hope to talk to you soon.